Assalamualaikum warahmatullahi wabarakatuh. Our topic is about the natural gas combustion control and Wobbe index. So I'm gonna explain briefly to you about the natural gas combustion control. So natural gas combustion control is actually has supplied our industries for many purposes such as steel and glass production. However, the composition changed by natural gases affect the environment in a bad way. So as we can see as example, glass industry and thermal treatment produce substances that are hazardous to our earth. Thus, however, some equipment had already been invented and introduced to solve this dangerous issue. So the next one we're going to about the Wobbe index. So what is Wobbe index? Wobbe index or Wobbe number is actually an indicator of the interchangeability of fuel gases such as natural gas and liquefied petroleum gas. Wobbe index is defined in the specification of gas supply and transport utilities. So the Wobbe index is actually used to regulate the flow of the natural gases to ensure the gas being used is consistent and that require the specification needed.
For the natural gas combustion and Wobbe index, there are 5 settings that we can do. For the test 1, setting at constant thermal input. For test 2, setting at variable thermal input and variable Wobbe index. For test 3, setting at constant Wobbe index. Test 4, setting at constant thermal input and constant Wobbe index. And for the last test 5, setting at prefix gross calorific value. For the test 1, setting at constant thermal input, the test is involved use of a test furnace fueled by natural gas of different composition in condition of constant thermal input to the burner and with natural gas flow rate regulated in accordance with variance in the Wobbe index. As we can see in the flowchart, full gas is supplied and going through the Wobbe index analyzer and through the thermal input regulator that has been set, and going through to the control valve and to the burner. For test 2 of the flowchart, setting at the variable thermal input and variable Wobbe index, the test is involved use of a test furnace fueled by a natural gas of different composition in condition of variable thermal input to the burner and with natural gas airflow rate regulated in accordance with variation in the Wobbe index, maintaining a constant furnace temperature and a constant stack oxygen level. As we can see the flowchart, which is a bit complicated, there are two supply. For the first supply is full gas supply, going to the Wobbe index analyzer and going to the thermal input controller, which is the temperature has been set to a constant, and go to the control valve and to the furnace. For the second one, combustion is supply going to the full to air ratio controller, which is the oxygen has been set to the constant and going to the control valve and to the furnace. At the furnace, the temperature and the state oxygen is at constant. For the third one, setting at constant Wobbe index, the test is involved use of a test furnace fueled by a natural gas of different composition mixed with air in such percentage as to keep the reference Wobbe index constant, equivalent to a value lower than the minimum Wobbe index for the gases used in the test. So for the flowchart, there are two supply, full gas supply and air supply. The supply is going to the flow meter for the percentage to keep the Wobbe index a constant, and the full gas supply is going to the burner and Wobbe index analyzer.
Okay, now I will continue for the test for flowchart at natural gas combustion and Wobbe index. So this test involve use of the test furnace fuel by pipeline natural gas in condition of constant heat input to the burner and mixture of the natural gas with air in such a percentage as to keep the Wobbe index constant. So this figure we provide at test 4, setting at constant Wobbe index and constant thermal input. So firstly, the first stage is the furnace was full with the natural gas from the network until it reached a steady state. And for the second stage, the control and the regulation system was activated and the gas was mixed with air. As only pipeline gas was available, the test was conducted by stimulating the switching between the different qualities of natural gas by setting the regulator to the different set value and of Wobbe index. In order to maintain the Wobbe index set point and the heat input set point, the system had to regulate the mixing air flow rate and the gas flow rate. So in this test, we performed the percentage of mixing as was varied. So this is for test 4. And we continue to the test 5. Okay, we continue with the test 5. So the test 5 was involved the test furnace full by natural gas of the different composition with the natural gas being mixed with air. And when the gross calorific value of the gas was higher than the pre-established upper limit, or with LPG, when this fell below the pre-established lower limit. So this is the figure provided for this test, that the setting at prefix gross calorific value. So for the first stage, it same like at test 4, the furnace was full with the natural gas from the network until it reaches steady state. And for the second stage, the control and the regulation system was activated and the gas was mixed with air or with LPG, with the furnace being filled with gas or different composition supplied from CNG tankers. Data of the Wobbe index, the behavior of the furnace and the control regulation system were then recorded and analyzed. That both for in the steady state. The aim for this test is to show the control and the regulation system was capable to maintaining the gross calorific value within a preset range despite variation in the composition of the fuel gas. So this is for test 5. Okay, now we go through the problem and issue that we get from the natural gas combustion and Wobbe index. So the accuracy of the instrument can be divided into firstly in random error and secondly is a systematic error. The two errors can cause the influence of external effects. So firstly, the random error that we get from the natural gas combustion is in order to determine the top to top noise level of this new instrument. A gas with a known Wobbe index was introduced to the meter and the signal of the oxygen sensor was registered. So this is first for random error.
Next is the systematic errors. Systematic errors refers to a type of error or bias that consistently affect the measurement or result of an experiment or study in a predictable manner. It is different from random errors, which each do the unpredictable variation and can be reduced by repeated measurement. Systematic error can arise from various sources, including flaw in experimental design, equipment calibration issue, environmental condition, or human factors. These errors can lead to measurement or observation that consistently deviate from a true value or introduce a consistent bias. The impact of systematic errors is cumulative and can significantly affect the accuracy and reliability of the data collected. Unlike random errors, systematic errors do not cancel each other out with repeated measurement and can distort the overall finding and conclusion of a study. Temperature can affect the Wobbe index because both of the heating value and the specific gravity of the gas can change with temperature. The heating value of a full gas is typically expressed in terms of energy per unit volume or energy per unit mass. As temperature changes, the density of the gas can change, which can affect the heating value. The Wobbe meter has placed in the insulated box, in which the temperature can be varied from 293 to 318 Kelvin in order to investigate the influence of variation in the environmental temperature on the measurement. The next is the pressure. The influence of variation of the pressure in the apparatus of the measurement has been investigated by intentionally varying the air supply pressure with the pressure regulator. The expected maximum deviation of the air pressure caused by the fluctuation of the pressure regulator and the influence of variation of the atmospheric pressure through the pressure regulator. So a maximum error occurs as a result of the air supply pressure variation is unexpected.
Assalamualaikum warahmatullahi wabarakatuh. The improvements and ways to overcome the problems are: firstly, training. Second, prepare written procedure for startup and shutdown. Third one, do regular and complete interval and fuel train tightness testing. And the last one, create corporate guidelines for third parties. First, training. Most of the explosions and fire incidents by far have been due to human error. All of the safeties and interlock equipments in the world wouldn't help if someone has bypassed or jumped out safety controls. There is no possible substitute for proper training. Training has been included mock upsets and hazard recognition drills. Next, written procedures. Startup and shutdowns are biggest risk. You need clearly written procedures that everyone understands and agrees with so that consistent safe practices are in place with every shift and every employee. Third, valve tightness testing. Make sure you do regular and complete interlock and fuel train valve tightness testing. Jurisdictional inspectors, even where they are mandated to be around, cannot be at your facility every day. Combustion equipment safety testing needs to be a part of your organization's culture regardless of what it costs and what its perceived hurdles are. It should comply with the court requirements for testing even if some inspector is not forcing you to. Next, and the last one is corporate guidelines for third parties. Create corporate guidelines for third-party combustion equipment reviews and commissioning for a newly acquired equipment or a major upgrades. Now that you see how little reviews and attention combustion equipment may receive from the times it's specified to when it's really operating, you may want to dedicate a professional review of the design and what you are getting by a qualified experienced third parties. Thank you. That's only from me.